Is group 3 not around?
Bottom down a group, and electron affinity increases from left to right across the periodic table and decreases from top to bottom down a group.
Okay, thank you so much, Sophie. So everything is actually correct. All right. So next, let's have group 6. We'll discuss B3.
For B3, why are noble gas electron configurations considered as stable? The electron configurations of noble gases are considered stable because their valence shells are fully occupied by valence electrons, which indicates that they do not require the need to react with other elements to lose or gain electrons because they are already stable and have complete valence electrons.
Okay, thank you so much. That is actually correct. So noble gases, non-reactive, always they are really considered as the most stable because of their 8 electrons, 8 valence electrons, which fully occupy their outer shell. Okay, thank you so much again. Group 6, let's proceed to group 7. You will answer B for A, B, and C.
Hello, good afternoon, everyone. Good afternoon, Miss. I am the current representative of Group 7, reading B4A, B, and C. So, uh, B4 reads, an atom of a particular element has an atomic number of 50 and a mass number of 119. The element finds applications in the formation of the metal alloy known as bronze and is also widely used as a protective coating to prevent corrosion. For A, it reads, how many neutrons does the nucleus atom uh, how many neutrons does the nucleus of this atom have? We answered 69 neutrons. For B, it is read out as write the complete electronic configuration of this element. The answer that we have written out would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5, and 5p2. For C, how many valence electrons does this atom have in its outermost energy level? We answered 4 valence electrons. And for yeah, A,
Okay,
B, and
yeah.
C. Yeah.
Okay, thank you
Sorry.
so much, Miguel.
Okay.
So again, everything is correct. So the 4 valence electrons, for those who are asking, asa nagslagikan, that is from your 5s2 and 5p2. So those are your 4 valence electrons. All right, proceeding to group 8, who will answer B4, letter D and E.
Good afternoon, Miss. In the strontium will have a larger atomic radius compared to the element of number 4, tin, Sn. And in E, strontium has a larger atomic radius compared to tin, since it has a lesser atomic number. The trend for atomic radius is that it decreases from left to right in the periodic table and increases from top to bottom as well. This is because as elements increase in atomic number, the number of protons also increases, therefore increasing the force the protons are exerting on the electrons, the effective nuclear charge, resulting in a smaller atomic radius. It also increases from top to bottom just because of the added energy levels for each succeeding row.
All right, thank you so much, Ryan. So due to the effective nuclear charge, okay, the pool of your protons to your electrons. So the more ang pull sa inyong protons electrons, it's gonna make your electron closer to the nucleus, and that also makes your atomic radius smaller. All right. Next, let's have group 9, who will answer the last question, which is B5.
Good afternoon, everyone. So for number 5, given the following elements, C and Ge, which is carbon and germanium, which belong to the same group and with the same element above symbolized in part B number 4 by the letter X, which means the tin. In number 4, it was being mentioned. So how do you think will the set of 3 elements be arranged according to decreasing atomic size? So both carbon and germanium belong to group 4A, which is the same with tin. So if we set the 3 elements in decreasing atomic size, it would be tin, germanium, and carbon, since tin has the highest atomic size, and which is 50, then preceded by germanium, which is 32, then carbon by 6. So that's it. Thank you.
All right, thank you. So any questions sa atong Okay, so kanina group assignment is actually ang purpose ani is for you to identify and to be familiarized with your periodic table. So you already know. I think while doing the assignments, okay, if you all really did it, you will know about the trends sa inyong periodic table. There will be a little bit of exceptions, but your periodic table, whether you go up or whether you go down, these have their own trends with respect also to their properties like your atomic size, your affinity, electronegativity, and so on and so forth. Okay, so I think I've already placed naman sa group assignment itself the allotment of points. Okay, so I don't need to anymore discuss the allotment of points. So let us now proceed to another, how do you call this, topic, which is your van der Waals bonding. Okay. So again, I will not be able to see your messages or comments there whenever I present Just wait for a while. Okay, so again, we will be discussing about your Van der Waals bonding. Okay? So if ato adyo ni siyang tukion, okay? And we are going to really determine the origin of these forces, the van der Waals forces. We will be needing quantum mechanics, but I don't want to deal with it, okay? It's too complicated. We will just present here a more simplified picture. So for example, if we have two electrical charges, positive Q and negative Q, for example, this is our charge. These are our charges. So this is positive Q and negative Q. And they are separated by a certain distance. Let us denote it as D. So we measure the distance from the center mismo sa inyong atom. Okay, so let's call that as D. We define our dipole moment as Q times D. For the equilibrium, atoms are actually electrically neutral. So your positive nucleus here is balanced out by your how do you call this? Electron cloud. Okay. Also, the centers of your positive charge, your nucleus, and negative charge electron clouds coincide. Therefore, when I say what is the dipole moment of a neutral atom? Neutral, so that would automatically give you a hint. So that a neutral atom has no dipole moment. Dipole moment is equal to 0. When a neutral atom is exposed to either an internal or external electric field, this could be caused by putting another charge, okay, near your atom. The atom may then become polarized. For example, if I put a positive charge near an atom, it is gonna attract the negative electron cloud, okay? And it's gonna separate your negative charge and your positive charge. So this creates or induces a dipole moment. I say induces because we created a dipole class, meaning duha ka poles, okay? Duha ka poles, so you have the negative pole, and you have the positive pole. So before, neutral sa yung atom, your positive and negative are just here, okay? Your centers are together. But when I introduce a charge, or when I expose it to an external or electric field, it created two poles, okay? Or it separated your positive and negative charges temporarily. So this creates, or this is what you call inducing a dipole moment. Okay, so you can see it here. This is an example, or this is your induced electrical dipole. Now, some molecules, your dipole moment does not have to be induced. Bale, it is already there. Okay? It exists by virtue of the direction of bonds and the nature of atoms that make up your molecules. What do we call these molecules na naanay dipole moment? We call them your polarized molecules. From the word itself, pole, okay, na siya different poles. Polarized molecules. An example of such a molecule that has a permanently built-in dipole moment is this. So what is this? You see 2H and 1O is connected to 2H and 1O. So this is just a dipole interaction between water molecules. Okay, so this is your water molecules. Molecules or atoms in which there is either an induced or permanent dipole moments attract each other. So depending, we have different types of van der Waals process depending on what molecules are involved. And the resulting force for this is known as the van der Waals force. Okay, your van der Waals forces between atoms and molecules have their origin in interactions between dipoles, which may be induced, or in some cases, interactions between permanent dipoles that are present in some polar molecules. So now let's talk about these different types of van der Waals interactions. The first type is what we call your London forces. Okay, induced dipole interacts with another induced dipole. That interaction, okay, we refer to them as London forces. An example for this is your helium atom. So these are two helium atoms. So as you can see, at first, there are even distribution of electrons, but since your electron cloud is constantly moving as well, there will be times that there will be temporary uneven distribution of electron, which causes a temporary attraction. So this temporary attraction gas, this is just gonna last for a very, very short time. Okay? Another type of van der Waals force, okay, is your Debye interaction. So Debye interaction, so when an induced dipole that is a dipole that is induced, what is otherwise a non-polar or atom or molecule, interacts with a molecule that has a permanent dipole moment, we refer this interaction as Debye interaction. One example of Debye interaction would be the forces between your water molecules. Okay, so your water molecules are the ones that are permanently polarized, and those of your oxygen molecules. So your oxygen molecules, mauna siya ang naay induced dipole moment. Okay, last but not the least, interactions. If the interactions are between molecules that are permanently polarized, okay, we call that as P-SOM interactions. Okay, P-SOM interactions. Again, these interactions arise when we have a permanently polarized molecule interacts with another permanently polarized molecule. Okay? An example of this is again your water molecules. Okay, so these water molecules. Okay, the attraction between the positively charged regions of one water molecule and the negative charged regions of a second water molecule. This provides an attractive bond between the two water molecules. The bonding between molecules that have a permanent dipole moment, or what is known as your P-SOM force. Okay, so this is your P-SOM force. Another term for this is your hydrogen bond. Okay, where hydrogen atoms represent one of your polarized regions. Thus, hydrogen bonding is essentially a P-SOM force and is also a type of a van der Waals force. Note that your van der Waals bonds are just called as secondary bonds. But the atoms within the molecule or group of atoms are joined by strong covalent or ionic bonds. Okay. For example, okay, how do we differentiate van der Waals heat your water to a boiling point? This already breaks your van der Waals bonds, kaning van der Waals bonds nimo. But ang imong makita ani is it changes your water into steam. Into steam. But with respect to the covalent bonds that are joining your H and O, that is your you need a higher temperature to break the covalent bonds that join the oxygen and hydrogen atoms together. So bali, although we term it as secondary based on the bond energies, actually your van der Waals forces, they also play a very important role in many areas of engineering. Van der Waals forces between atoms and molecules, they play a vital role in determining the surface tension. And my example, your boiling points of liquids. And in material science and engineering, the surface tension of liquids and the surface energy of solids come into play in very different situations. For example, if you want to process ceramic or metal powders into dense solid parts, the first step of this is to mix the powders. Okay, the powders often have to be dispersed in water or organic liquids. Whether this can be achieved, kaning effective dispersion, the achievement of the effective dispersion, this depends upon the surface tension of the liquid and the surface energy of the solid material. So, bali, there is a theoretical formula actually to already predict or to determine your surface tension and your surface energy. Surface tension of liquids also assumes importance when we are dealing with the processing of molten metals and alloys, for example, sa casting process, and also glasses. Van der Waals bonds can actually dramatically change the properties of certain materials. So, for example, we have graphite and diamond. And in many plastic materials, molecules contain polar pairs or side groups. And van der Waals forces also provide an extra binding force between some chains of polymers. For example, you have your polyvinyl chloride or PVC, where your chlorine atoms, okay, it's already labeled there, your chlorine atoms, kaning blue, these are attached to the polymer chain, have a negative charge, and the hydrogen atoms are positively charged. So the chains are weakly bonded by van der Waals bonds. This additional bonding makes PVC stiffer. However, if you apply a force, okay, when you simply apply a force to the polymer, for example, we apply a force to the right, okay, to the left. So the van der Waals bonds are broken and the chains, as you can see, they slide past one another. Okay, you can see the sliding motion. Now, let us talk about binding energy and interatomic spacing. So interatomic spacing, this is the equilibrium distance between atoms, and it is caused by a balance between the repulsive and attractive forces. In the metallic bond, for example, the attraction between the electrons and the ion cores, this is balanced by the repulsion between the ion cores mismo. Equilibrium separation occurs when your total interatomic energy, or IAE, of the pair of atoms is at a minimum, or when no net force is acting to either attract or repel the atoms. So the interatomic spacing in a solid material, it is labeled here. This is approximately equal to the atomic diameter or twice the atomic radius r. We cannot use this approach for ionically bonded materials. So, however, since the spacing is the sum of the two different ionic radii, okay? Here, a material that has a high binding energy will have a high melting temperature and a high strength. So, what do we mean by minimum energy or binding energy? Binding energy, sometimes called as the minimum energy, this is the energy required for you to break or create the bond, okay? The energy required to create or break the bond of your constituent na atoms. Consequently, materials having a high binding energy also have high strength and a high melting temperature. Okay, so ionically bonded materials, they have a particularly large binding energy because of the large difference in electronegativities between the ions. While metals, on the other hand, they have a lower binding energies because more or less, ang electronegativity sa mga atoms, they are more or less similar. So let us compare the binding energies for the four bonding mechanisms. So our binding energy, the unit used for binding energy is K kilocalorie divided per mole. Kilocalorie per mole. Okay, first, ionic. Yung binding energy is 150 to 370. How about the covalent bond? We have binding energies ranging from 125 to 300. Metallic bonds, we have from 25 to 200. So, asa man ang van der Waals? Pila man ang van der Waals, ani? Because we already stated na, this is just a secondary bonding mechanism. It's very small. So, this is actually just less than 10 kilocal per mole. Okay. Now let's proceed to the modulus of elasticity, yield strength, and coefficient of thermal expansion. So these variables, these properties are very useful when you are dealing with different materials. For instance, some material science and engineering, most of the time, the modulus of elasticity, yield strength, and coefficient of thermal expansion are quantified. So other properties that can be related to the force distance and energy distance expressions. Okay, for example, we have your modulus of elasticity of a material. So for example, you have this force versus separation curve or force distance curve. Okay, if you get the slope, tangent to the curve, and those are your modulus of elasticity. That is the slope of the stress strain curve in the elastic region, and it is also known as your Young's modulus. Okay, a steep slope, steep means more or less paduna straight. Okay, a steep slope. This correlates to a higher binding energy and a higher melting point. This means that there is a greater force required for us to stretch the bond. Thus, the material has a high modulus of elasticity. An interesting point that needs to be made is that not all properties of engineered materials are sensitive to their microstructure. I know that I've already said before na microstructure sensitive ang mga engineered materials, but not all properties can be affected by microstructure. What do I mean by microstructure? Kanaging whenever you look a material into a, for example, scanning electron microscope, you can see the grains mismo. Okay, mga pores. So those are your microstructure. One property not dependent through the microstructure is your modulus of elasticity. Okay, so for example, you have two aluminum samples. They have essentially similar chemical composition, but through the difference of their processes, the synthesizing processes nila, it will have different grain sizes. Do we expect the modulus of elasticity to be different as well? No. We expect the modulus of elasticity of the samples to be more or less the same. However, imuhang yield strength, okay, the level of stress at which the material begins to permanently deform, these samples will be quite different. Okay, so yield strength is therefore microstructure sensitive property. Compared to other mechanical properties such as yield strength and tensile strength, ang imuhang modulus of elasticity, no need to know the microstructure. It can be linked directly to the stiffness of bonds between atoms. Thus, your modulus of elasticity depends mismo what atoms make up the material. So if you know the atoms that make up the material, no need to synthesize or anything, you can calculate na mismo diretso ang imuhang modulus of elasticity. Another property that can be linked to the binding energy or interatomic force distance curves is the coefficient of thermal expansion, or what we call CTE. This is often denoted also by the Greek letter alpha. Okay, this is the fractional change in linear dimension of a material per degree temperature. Your coefficient of thermal expansion, or CTE, this is related to the strength of your atomic bonds. Atomic bonds, okay? In order for the atoms to move from their equilibrium separation, in order to break the atoms from their equilibrium separation, we must supply energy to the material. So as you can see here sa akwang illustration, this is already curves of interatomic energy versus separation curves. So a very deep interatomic energy here, this is the deepest point, caused by strong bonding, is characteristic of the material. Then the atoms separate to a lesser degree and have low linear coefficient of thermal expansion. Materials with a low coefficient of thermal expansion, they maintain their dimensions more closely when the temperature changes. So what are the applications ng ani atong materials with very low expansion? They are useful when you need components that are expected to repeatedly undergo relatively rapid heating and cooling. So sa ceramic research man ko and material science man akong specialty. So when you make ceramics, you actually subject it to rapid heating and cooling many times. Okay, so you need a material that has good CTE. Okay, for example, aning ceramics will be your core diorite ceramics. These are used as catalyst support sa mga catalytic converter sa cars. You also have your ultra low expansion glasses, your ULE, and it's the visionware, and other glass ceramics developed by Corning. They all have very, very low thermal expansion coefficients. As you can see, very important ang imuhang to draw the curves. Okay, the interatomic bonding energy versus separation curve, the force versus separation curve. From these alone, daghan na kay kag properties na ma-compute, daghan na kay kag properties na ma-determine. All right, so far, any questions?
None, miss.
Okay, thank you for response. So we will be ending this lecture here. So yeah, I'm gonna post this later, but not the PowerPoint because I know maglibog mo na. So I'm gonna post a more legible handout about our discussion for this day. Okay, so next, your next meeting will be on Thursday. So you will have asynchronous learning. You will be learning about the carbon. Okay, the different forms of carbon. So I think if nakabantay mo sa balita aron or sa trends sa science, there are actually carbon is getting the attention of the town. Okay, so we have our graphene. So sikat ni siya, I think for almost 10 years now or 5 years. Many people are still experimenting on this material. It's said to have a very, very high strength material. And imagine, one layer only of carbon chain. Okay, just one layer can help you create a very, very strong material. So for your asynchronous meeting, you will be learning about the many forms of carbon, the atomic and ionic arrangements. So na short range order, you will know about that. What is short range order, long range order? We have our defects sa inyong atoms. Okay? And these defects actually, these mostly occur during the synthesis of your material. Okay? So when you synthesize a material, depende sa procedures like for mixing the powders or sa pag-transfer lang sa inyong material from one equipment to another, the environment, the air outside, if it's oxygen or nag-neon gas ka, those can induce impurities. And consequently, it will also change the properties sa inyong material. Alright, so far, any concerns or questions?
No, no questions, miss.
Yes. Okay. I think that's it. And thank you so much, class, for attending this meeting and see you next week. Bye-bye.
Thank
Goodbye, miss. Thank you.
Bye, miss.
Fine, thank you, miss.
Goodbye and thank you, miss.
Miss,